Well, hello everyone. Thank you so much for joining. This is a very special first Brownback session of our 2022-2023 year for the NCME GSIC Brownback sessions. And today I have the honor to invite and present my advisor, Leslie Rutkowski, who's a professor of qualitative and quantitative research methodology at Indiana University. Leslie's research is in the area of international large-scale assessment. Her interests include latent variable models and examining methods for comparing heterogeneous populations in international surveys. Recently, she completed a Norwegian Research Council grant on developing international measurement methods. And also she has published the Handbook of International Large-Scale Assessment with Matthias Bondavir and David Rutkowski. Leslie currently serves as associate editor for the Springer Journal, Large Scale Assessment in Education, and as a co-executive editor for the Springer book series, IEA Research for Education. She's also the chair of PISA DAG, the Technical Advisory Group, and NAEP Questionnaire Standing Committee. So without further ado, I'll mute myself and pass the mic to you, Leslie.
Thank you, Monza. Thanks everyone for the invitation and for a chance to talk about some of the work that I've been doing with collaborators over the last few years, and also a topic that Monza is building on for her own dissertation. So she'll probably have some thoughts as well on some of these things. Mine's the only name here because I'm presenting, but the work that I've done in this area is in collaboration with several colleagues. So it's not my own, although I'll take responsibility for anything that you might criticize today. Okay, so Monse asked me to come and talk a little bit about multi-stage testing and international large-scale assessment. So that's what I'm going to do. I'm assuming that people are coming maybe with varied backgrounds in terms of their knowledge about international large-scale assessments. So I want to provide a little bit of an overview and also a context for why I'm interested and why I think this is a methodological playground to work in international large-scale assessment. There are so many complexities, so many open questions, and so many areas for research that you'll never run out. Okay, so a very short history. The IEA, which is the International Association for the Evaluation of Educational Achievement, this was a group that came out of the United Nations following World War II and part of the Marshall Plan to help rebuild Europe. And so the IEA is a group of educational researchers. So Bloom was part of this, from Bloom's taxonomy. There are some other names that are more well-known to European researchers, but it was this group of people in like the 50s and 60s that thought the world is an educational laboratory, and they wanted to see if they could collect data internationally to see comparatively how countries perform in a number of areas. Now, this sounds pretty trivial now that we have technology and in a much more modernized society than things were back in the late 1950s, early 1960s. But this was a huge undertaking. I mean, people communicated primarily by snail mail. If they had a budget, they could make a phone call. Things moved much more slowly and coordination was much more challenging. Of course, everything was paper and pencil. They measured in math, reading, geography, and science. And you can see the rest of the details here. The world looked very different at that time, and especially European countries. Germany was divided into East and West. Yugoslavia, which is now a number of countries, including Slovenia and Croatia and Bosnia and all of the Balkan countries. So you can see that the participants, primarily European, along with the US and Israel. And so, like I said, this was really a feasibility study, sort of a adventurer's brave work to see, could they do it? And out of the pilot study report, they said if the results so far, because of limitations on their validity, which the authors freely admit, and I'm highlighting this because this early data sometimes gets used in ways that I find to be inappropriate. I'm not going to talk about that today, but the frameworks weren't well developed. The sampling was pretty dodgy, and there were a lot of issues around this first feasibility study. But they said, although the findings might be only suggestive, at least they offer real encouragement for believing that such results can in the future lead to more significant results. And this really, not this quote, but the results from this study really opened the door for a series of studies that followed. The next was the first international mathematics study, followed by the 6-subject survey, and then the second international mathematics study. For those of you that know a little bit about US educational policy, the SIMS study was the basis or provided some of the impetus for A Nation at Risk, where they said that the US was suffering from a rising tide of mediocrity. And this was partly because of the space race with Russia and the feeling that we were being left behind in science and technology. And the results from the second international mathematics study really formed the basis for the push in the US to build up STEM research and to put resources behind that. Okay, so then we have the first modern era. We're going to take another shift in a bit, but in 1995, well, prior to that, Bob Mislevy and his colleagues worked at developing, integrating item response theory into assessments, as well as what we refer to now as plausible value methodology, latent regression, dealing with matrix sampling and only giving part of a test to examinees and still being able to generate population level estimates of achievement. So all of this came together in like the late 80s. They implemented it in 1995 in TIMSS. And the advance here is that the sampling was much improved. The frameworks were much improved. So it is representative in terms of the populations that took part in 4th and 8th grade. They use these rotated booklet designs, as I said, where they only give part of the test to each examinee. They used IRT and population modeling methods, and it measured the curriculum. In 2000, PISA took a slightly different approach in that rather than being grade-based, they focused on an age-based sample. And they wanted to emphasize students' ability to use their knowledge and skills to meet real-life challenges. So this was really in the late 90s, early 2000s. They had intended it as being like a test of workforce knowledge and how ready youth was to participate in society. So that brings us to where we are now. The studies are increasingly computer-based because of technology and because we can, and it's a lot, it opens a lot of doors in terms of what we can do. They are increasingly adaptive in various ways. They're also measuring a lot more on purpose. So PISA introduces an innovative domain in every cycle. There are also a lot of optional questionnaires that have been added. And then there's also measuring a lot more as a side effect. Because the tests are computer-based, we now have process data, all the information that comes from mouse clicks and page turns and how long you spend on a question. So all of this data are available. And there are new models and methods to understand test-taking behavior as a function of not just whether you got the answer right or wrong, but how long you took and whether you corrected your answer or changed your answer. Okay, so the purpose of the assessments, what are these trying to do? TIMSS and PISA are the biggest international assessments, and their aims and orientations differ a little bit because of the organizations that host them. But TIMSS, it's math and science, and it's the math and science that students are expected to learn as defined by participating countries' curriculum policies. PISA is different because they say they are not based in any curriculum at all. And it's what the OECD regards as essential for full participation in modern societies. Now, I could spend time talking about this and problematizing what it means for an economic organization to dictate the way education should look internationally, but that's another topic. So anyway, they are representative. In general, the studies are comparable across all the countries that participate, and you get measures of trend. A note on participation, because this also speaks to some of the methodological questions and some of the exciting areas that are fun to do research in. Since 2000, and I'm going to focus on picking on PISA here, but TIMSS has also experienced its own growth and changes in the number of participants. Okay, so if you don't know, the OECD is a group of industrialized, wealthy member countries that are focused on the economic well-being of participants. So in 2000, there were 28 OECD countries that participated and 15 non-OECD countries, or what are called partner countries. And these tend to be less economically developed, although not always, because Taiwan is not an OECD country, but it is industrialized. And then just tracking across these two rows, you can see that because the number of OECD countries has increased, the number of OECD participants has also increased. But what's really striking is that the number of participating countries from non-OECD countries, although the test was designed for OECD participants, these partner countries have really, really grown. You can also see that as a function of that, that achievement has also changed a bit over time. In terms of, like I said, math is a little bit more striking. You see like more fluctuations up and down as the number of countries grow. And then also the GDP per capita in the non-OECD countries, you can see is vastly different than the average GDP per capita of OECD participants. So that is to say that these are very heterogeneous countries, very different from one another. Non-OECD countries tend to be very different from OECD countries. Now, thinking about this from a measurement perspective, there's language, there's culture, there's economic development. All of these differences play a part in the way in which you measure and the way in which they understand what they're being measured by. We have new participants. Now, this is just 2018. 2022 is taking place right now, but in 2018, you can see the list of new participants that are very different from Germany, the US, Canada, France, and so on. Again, in terms of economic development, in terms of language and culture. One note, Belarus is out because of the war between Russia and Ukraine, and the Belarusian unqualified for support for Russia. Russia was kicked out and Belarus was kicked out. What about IEA studies? So like I said, I'm picking on PISA because they're currently experiencing the most growth, but IEA studies are growing too. In 2019, they added Pakistan, the Philippines after a 16-year break, Montenegro, Kosovo, and Bosnia. And Bosnia was after a 12-year break. Okay, so a little bit on, that's the background on international assessments. Now something about adaptive testing in international assessments. The motivation for this talk and some of the research that I'm doing is in this area of international assessments and multi-stage testing, what it can do, what it can't do. The background is that in 2011, the OECD's Program for the International Assessment of Adult Competencies, or what's known as PIAC, implemented the first adaptive international assessment in form of a multi-stage test. The two key reasons that they did that were because it gave an improved assessment experience for participants. You better matched the difficulty of the items or group of items to the proficiency of the examinee, leaving very clever students or clever participants feeling like they're being challenged, and less clever or struggling participants given easier items so that they don't feel defeated. They're more accurate and valid population estimates for many participating systems. And then there's another issue that is going to come up in some of the simulation studies that I'm going to talk about, and that's item exposure. Now, in a lot of computerized adaptive testing, we're worried about item exposure because of test security and cheating. And if items get exposed too much, then the populations of examinees will know the item, they'll know the answer, and then it's useless. So item exposure in international assessment is a little bit different because of this cross-cultural component, because all of the countries are taking the tests. Now, lower performing countries will tend to get easier items more often than other countries, and very high performing countries will tend to get harder items more often than lower performing countries. This can have an impact on item parameter estimation, especially the discrimination parameter. So there is a desire to have even item exposure, or reasonably even item exposure across the country, so that we get good item parameter estimates. That's another issue. So in most multi-stage tests, item parameters are known, and we have an item bank. This is not true in international assessment. Item parameters are only estimated after data collection, which has a number of consequences, but one of those is, like I said, we don't know. The tests are assembled based on interim estimates of item parameters, but we don't know them in advance. Okay, so just very briefly, what is multi-stage testing? It's adaptive, but it's not fully adaptive. It lays somewhere between a linear test and a full item level CAT. Rather than a full CAT where the next item selection is based on performance on the previous item, MST is built in modules, and the next module selection is based on performance on a previous module. And I have just a figure here. So how it works, and especially in PISA, how it works, and in other studies. Now, this is one design that doesn't exactly match the PISA design, but it gives you a rough idea. So examinees start at stage 1, or what's referred to as the core. Based on how they perform on that, we estimate an interim proficiency value, and then there's a decision made about whether they should go to a higher block of items in terms of difficulty, or a lower block of items in terms of difficulty. At the second stage, depending on performance, again, they're either routed high. Here, I have the option for medium or an easy block of items. And then based on the responses, we estimate the final proficiency value. Here I have a single panel. You can have multiple panels, and this is the approach that PISA has taken. They have a number of panels. You can link across the panels, and this is just one design. There are lots and lots of designs that are possible. The design that I have here is what's called a 3-stage 1, 2, 3 design, because you have 1 block of items at the beginning, 2 in the middle, and then 3 at the end. So what are the advantages? They're similar to item level CAT in terms of improved efficiency, maybe not the amount of efficiency that's improved, but they improve efficiency. They improve precision. And like I said before, they give you an improved test taking experience. What's really my interest in international assessment is that you can target the full achievement continuum, and the test can be tailored to needs of test taking populations. Why does that matter here? Here I have the distribution of achievement for PISA in 2015 for science. And I put this back on a Logit scale where it's distributed 0-1. So we have participants from dozens and dozens of heterogeneous populations. And you can see that from the very lowest level of achievement up to the very highest level of achievement, that there is a big span across the theta continuum. And so then it starts to raise the question, because there are different languages and cultures and economic development, and now we see very, very different levels of proficiency, is one test suitable for everyone? So in this setting, we have a lot of questions, loads and loads of questions that you can ask about how to design a multi-stage test. And we took up a couple of these in 2 studies that I'll review here. So one of the things is how to route. What threshold should you use? So if I give you 8 items, should it be if you get 4 or more? Should it be 5 or more, 6 or more that dictates if you go to a harder block? What method should you use to route? And how to estimate an interim theta. Should you use classical test theory, just number correct, or do we need IRT? Should it be based on all previous modules? So once you're going from the second to the third, should we count 1 and 2, or should we just count 2 to make a decision about 3? And then how to design the test. So what general design? I showed you one possibility. How many panels do we need? What should the module length be? Do we need 3 items? Do we need 20 items per module? And then how should the item parameters be distributed? This is absolutely not exhaustive. And like I said, we have challenges. The systems are very, very different. The participants in these international assessments are very different. This could bear out in the test, and it does. We see it empirically that there is diff that is due to culture. And we also see differential engagement in the tests. So here briefly is the MST design that was implemented in PISA 2018 for the major domain. So this is for reading. You can see that there are lots and lots of pathways, and this is just one of the 2 designs that they used. So you start with a core block of reading items, and I'll just focus on RC1, so reading core 1. Based on your performance, if you follow the 2 red arrows, you can either go to a high block R11H or R15H, or if you don't do as well, then you go to R11L or R15L, and L and H stand for low and high respectively. Then depending on which of those 4 you go into, and then also depending on your performance, then you're routed on to a final module of items that are either high or low based on performance. What they found through this design was that measurement precision was improved by 4 to 5% in the middle. And then out at the ends where we're really concerned because of high and low performers, there were gains in precision of up to 10%, which yay, right? But don't get too excited because sampling error accounts for 95% of the standard error. So you're cutting out like 5% of the pie is measurement error, and you reduce that by somewhere between 4 and 10%, which is desirable. Of course, we would like to limit uncertainty, but the amount that we can cut out is maybe not that much still. Then PISA 2022, which is taking place right now, they adjusted the design a little bit, and I'm going to talk about this in a couple of places. I just want to raise it now. So this issue of item exposure, so that countries, low performers will see hard items, high performers will see easy items. They introduced something that I'm going to come to in a bit that I call probabilistic misrouting. So regardless of how you do on the core block of items, you have a chance, a small chance of being routed into an inappropriate module. So let's say you get all the items right in the core, which certainly means that you should either go to R11 high or R15 high. There's a chance that you will instead be routed to a low block of items so that we can get even item exposure. And the same applies for, let's say you got no items right on the core. There's a possibility that you'll still get routed to a hard block of items to ensure even item exposure. Instead of doing that misrouting, what they're doing in PISA 2022 with the math items is, so here you can see, let's just focus on group A with item set 1. You take a core block of items, and then you either are routed into a harder set, depending on your performance, a low set, depending on your performance, or you have a chance of being routed into another core block, which are moderately difficult items. Same story, if you get routed into that core block, then you continue on to a core block or moderate set of difficulty items. So this ensures that we're getting reasonable item exposure while also not misrouting students. So just a slightly different approach to controlling item exposure. PISA 2025 is the next cycle. We have a new contractor. It used to be ETS from 2015 until 2022. ACER was the previously Australian Council for Educational Research, was the original contractor from 2000 to 2012. They got the contract back. They're going to implement the multi-stage test in science. It's in the early stage of development, but it looks like the design is going to be almost exactly the same as PISA 2022. All right, so all the background, then I'm just going to briefly review a couple of papers that I have collaborated on in this area. So this idea of probabilistic misrouting. As I said, one of the questions that we have is how to route. And in the ILSA context, we talked about there's some concern that hard items are going to be overexposed in high achieving, easy items are going to be overexposed in low achieving countries. Biased parameter estimates, especially discrimination, and possibly because of that, we might wind up with biased achievement estimates. So this idea of probabilistic misrouting, as I mentioned before, it's usually merit-based, but if examinees have some probability of going to the wrong module, then hard items will get exposure in low-performing countries and vice versa. So we considered this. And based on an extensive simulation study that I did with several colleagues, what we know or think we know was that in a single population where we assumed that theta was normally distributed 0, 1, with a 3-stage 3-2-1 test and a single panel with 36 items per route and test and IRT information-based routing, we found that there was little difference between fully merit-based and probabilistic misrouting at 0.3 or 0.2 versus random routing in terms of bias in person parameters, difficulty, or discrimination. So it didn't matter a ton. But what we didn't consider was that PISA has multiple populations. We also only looked at a single panel, and we used EAP as an estimator for theta rather than using the methods that are operationally used in international assessment, which is closest to Worm's method, but a better approach is the plausible value methodology using latent regression. So we took that approach. So this is an article that just came out this year in Applied Psychological Measurement. So like I said, we updated our previous work with multiple populations, with multiple panels, and we drew plausible values from a posterior distribution. So a little bit of an overview on what we did. It was a simulation study. We used as the basis the empirical performance of 3 high-performing, 3 middle-performing, and 3 low-performing countries. You can see their means on the scale, the TIM scale, the standard deviations, the sample sizes, and then we standardized the means back onto like a closer to a logit scale. And we also had to cut the sample sizes in half because the package that we were using to simulate the data was agonizingly slow. Monza, you've had experiences with this, unfortunately. And so the only recourse that we had was to cut the sample sizes in half to speed things up a little bit. We used a 4-panel design where we had core block, and then high, low, high, medium, low. And like I said, we had 4 panels that were all linked together so that we could get population estimates for every group. Just briefly, the item distribution. So for each one of the low blocks, we tried as best we could to make sure that the mean location were about the same between low, medium, and high. We used equal module links of 12, 12, 12. Here again, you can see for low, medium, and high for the slopes, we tried to get those as close as possible. They're a little bit more off because we prioritized item difficulty, but we got them as close as we could. And then you can look to see that the test item information is, they're relatively similar across the panels. So how did we conduct study 1? In each population, examinees were randomly routed to a panel, and then each module, which is 12 questions, gives us a 36-item test. In study condition 1, we looked at 3. In study 1, we looked at 3 different conditions. We had random assignment. So as it's operationally done before multi-stage testing was implemented, then we used fully merit-based routing that was based on IRT information. And then we also used IRT information with a 30% chance of misrouting. So the split at stage 2 was 0.3 times 0.5 probability of going to one of 2 wrong modules because there were 3 possibilities. We simulated the data using the R package MSTR with a modification that David Magus very kindly modified to include this probabilistic misrouting element. And so based on item responses from step 1, we generated plausible values using TAM. We set the scale in the first country to have a normal 0-1 distribution. And then we used a mean transformation to put item parameters back onto the generating scale. Those transform item parameters were treated as fixed in an empty latent regression. And then we drew plausible values from that latent regression, and we repeated each condition 100 times. Just to make sure that things were functioning well, we wanted to look at the path distribution, which was okay, no problem. And so what did we find? First, we're looking at the generated slopes on the x-axis and the estimated slopes on the y-axis. And the chatter that you see is the variance across the replications. So the diagonal line means that the generated slope and the estimated slope were the same. And we don't really see any bias here, which is good. But we do see that there's a lot more variability in replications for merit routing, from random assignment to merit routing. And probabilistic misrouting was pretty effective at reducing that cross replication variability. That's in the slopes. We saw a little bit the same thing in locations. You don't really see a whole lot of differences between the two. There's a little bit of an increase in the variance in merit routing. Probabilistic misrouting brings that back down. So it works really well at adjusting for those things. So then the question is, if we got good item parameters, what's the impact on proficiency means? We found for high-performing countries that there was very little impact depending on random assignment, merit routing, or probabilistic misrouting in terms of estimating proficiency. Same for mid-performing countries. But in low-performing countries, you see with merit routing that we overestimate a bit performance in the low-performing countries if we use merit routing. Random assignment gets us back, but we want to move on and be able to use multi-stage testing. So the best way to go to attend to these slight biases is to use probabilistic misrouting. So our conclusion was that all the methods recover item parameters reasonably well. Merit routing produced the most slope variation across replications. And although the mean was fine, it's possible that you could wind up with bias slope parameters for any single estimation, any single draw of a sample of examinees, and any single estimation of item parameters. So it's possible that you can bias your slope parameters, and there was a relationship between the magnitude of the slope and the variability across replications. Locations were recovered really well regardless. And as I said, there was a slight positive achievement bias in low-performing groups for merit routing. Our second study was looking at relative module length. And a key consideration here is that in any test design, we want to administer as few items as possible to achieve whatever our outcomes are. And here it's stable, sufficiently precise population achievement estimates. We're not interested in estimating achievement at the individual level. So we asked if shorter initial modules lead to greater routing errors and subsequent problems with achievement estimation. And do balanced versus unbalanced module lengths demonstrate any advantages? And then do routing methods matter in a multi-group context? So here we looked at just the merit routing approach, and we looked at whether we should estimate the interim theta using classical test theory or item response theory. We took a cumulative classical test theory approach, and we used Fisher's information from IRT. We considered designs where we had 12, 12, 12 items, so 12 in the first core, 12 in the first stage, and 12 in the second stage, or 6, 10, 20, 20, 10, 6, 6, 20, 10. 4 panels, same as before. Here you can see a little bit of the test information distribution based on the study design, and a little bit of what we found. So if the modules have equal length, so here's our generated slope, equal length modules with random assignment, we wind up with the least amount of chatter. If we use IRT routing, we see that there's a little bit more variability. With CTT routing, we also see that there is a bit more chatter across the replications. And you can see that depending on equal length, short to long, long to short, and short, long, short, that the best is the long to short approach, where across the 3 different implementations of routing to the next module, there's the least amount of variability across the replications. That's generated slopes. In generated locations, we see a little bit different results than we did last time. So random assignment has the least amount of variability across the replications. IRT routing has a bit more in general. And then CTT routing, especially out at the more difficult items, you see a lot of variability in replications. Again, this long to short approach is the one that reduces that the most. Then in terms of estimating proficiency, there's a lot to look at here. I'll just kind of highlight that we see a little bit of overestimation in the lowest performing groups, regardless of the methods, and that it was the least for random assignment. And there weren't really any differences between IRT and classical test theory. One nice thing about that is the programming that has to go into designing a multi-stage test. It's more complicated if you're going to estimate theta based on IRT versus using just number correct. So that the results weren't really different between IRT and classical test theory from an operational perspective is nice. So we didn't see any slope or location parameter bias. Of the 2, IRT routing produced a little bit less variation across replications, and especially for difficult items, there was the lowest variation for IRT routing. We also didn't see slope or location parameter bias that was based on module length or arrangement. Long to short had the lowest variation across replications, but logistical constraints make this kind of a challenge. So the way that these booklets are, or the panels are assembled, the modules are assembled, is that the organizations like to have equal lengths, because there are switches in the way that the study is designed. So something that is a stage 1 group of items in one design winds up being a stage 2 group of items in the next design. So changing the length of the modules is logistically challenging. Achievement parameters are well recovered, but we see that low performers wind up being overestimated a little bit under either type of merit routing. So then I'm going to close with just a final note that, as I said before, rather than probabilistic misrouting, PISA has moved on to have some fixed proportion of examinees that basically take a linear exam. Now, that's not to say that there aren't other international assessments out there that are thinking about using computerized adaptive testing. So these findings can still inform them as they're thinking about different designs that they might take up as they're moving into this digital adaptive world. Okay, that's all I have. And I'm happy to take questions and give you any more information about what I've done.
Thank you, Leslie. This was very comprehensive. I really enjoyed it.
And fast. maybe rather than like normally when I'm watching videos, I'll speed it up to 1.5. Maybe you have to slow it down to like 0.5.
Oh, well, thank you so much again. Does anyone have questions? You can either raise your hand, and I'm gonna change the view to
Oh, and I can stop sharing so we can see each other's faces a little better.
Thank you. Okay, so if anyone has any questions, you can either type them on the chat or raise your hand. I'll be happy to. And while we wait, I do have questions. So this new PISA 2022 design, what are the expected, I guess, expected benefits and also limitations that probably you discuss in the TAC meeting, if you don't mind sharing? Because the fact that we're going from core to core, or like medium, and trying to absorb all the misrouting effects, I wonder if it also is not showing the benefits of item exposure and other things that you've shown through your papers.
Yeah, so Peter Van Rijn is the psychometrician that did a lot of the work, and Hyozhong Shin, both ETS researchers. They had done most of the simulation work on this. And what they found was it worked really well. And it did a nice job of estimating good item parameters, estimating good proficiency values. And the two papers that we did with probabilistic misrouting, we used like just a really very simple approach that it was either like you had a 0.2 probability or a 0.3 probability of being misrouted. What was done in practice in PISA, and you can look at the technical reports from 2015 or 2018, there was this probability layer. And it depended on your performance level. What else did it depend on? So you had anywhere from like, say, a 0.2% chance of being misrouted up to like a 0.17% chance or point. Anyway, there was so much complexity to it that this really alleviates that there's a chance. And I think in the end they settled on, I forget the last TEG meeting we had. I can't remember if they went with 0.2 or 0.3, but it's just straightforward. Just a random draw, either 0.2 or 0.3. You're either routed correctly based on your performance, or you just continue on with a linear test.
Interesting. Interesting. Okay, so Yahweh Shen, you have a question? I'll read it, but if you want to mute yourself, please feel free. Have you compared the bias for the proficiency between students who are misrouted and students who are routed correctly?
No. Although I did look empirically. And I mean, we don't know because it's just it's an observational study, but I looked at the performance of people that were misrouted, and it doesn't have any impact. And Janine Buchholz, who works at she's a staff member at the OECD. She also looked at motivation, depending on whether or not you'd been misrouted or not. And again, empirically, what she found was like this misrouting didn't really seem to have much of an impact, which, I mean, in that end, it kind of defeats the purpose of the multi-stage test, right? Like, those kids don't seem to be really impacted one way or another. Okay, precision goes up, yes. There are benefits, but it doesn't seem to have much of an effect on the test taking experience of the examinees. Follow-up question. Nope, there are no stakes to the student at all whatsoever. It's a very, very, very low stakes. In fact, results are not reported at the school, class, or student level because of this design, because you only get part of the test. The precision around student level estimates is the standard errors are enormous. You have no idea what a student actually knows. And it's not a goal of any of these studies to say anything about individual students, classes, or schools. It's really about country level results and then subpopulations within the countries. And you'll also notice that, like, if you study a little bit about CAT, there aren't any stopping rules. It's not like you take a test until your standard error gets down to some level. There's zero concern around individual level standard errors.
Got it. Thank you. Yeah, I was just curious because I know like the advantage of a CAT is to bring up the precision. And if we misrouted student, then that the improvement in precision is lost. Yeah. But it's interesting in this scenario of this type of test where student doesn't really have there is no impact on student level. So I feel that's interesting. I feel like this misrouting is probably very applicable for this type of international large scale assessment, but not for a school level or state level MST test.
No, and really, like I said, there's a trade-off, right? You want to get good item parameter estimates, and this is one of the, as I said, like at the very beginning, item parameters aren't to score populations of examinees. item parameters aren't estimated until after data collection. So that's where this concern about item exposure really plays a big part. And there's a desire to evenly expose items across the population. Otherwise, it does have an impact on discrimination, and you can wind up with some really strange results.
I have a follow-up question for that. Then this was a great presentation. It was really clear, concise. Thank you so much, Dr. Rutkowski.
Yeah.
I was going to say, when you're estimating the interim proficiency estimates in an adaptive setting, then if we are waiting until after the exam is done for estimating the parameters, are we using the interim range of the item parameters to start with? Like how does that happen?
Yeah, so the item parameters that are used to assemble the modules come from, so there's a field trial that takes place before the main survey. And so they get interim item parameters based on that. And then also about a third of items on any cycle of PISA or TIMS are trend items. And they have reasonable confidence in the stability of those item parameters. They're re-estimated every cycle and tested to see if there's been drift, but they generally have a very, very good idea about what the trend item parameters are going to be. And because of the field trial, they use those as like interim item parameters to assemble the modules. And then they just use classical test theory for routing.
Oh, okay. They don't use IRT-based models for routing.
No.
That's interesting. Okay.
Yeah. And also there are some like constructed response items that are in these, of course, and those don't figure also into routing.
Okay.
Oh, and then I forgot to say one thing that like, this isn't really particular to multi-stage testing, but a real step forward, I think, in PISA 2022 was that they used linear programming to optimize the assessment design based on like, it was really tough too, but based on like 6 different criteria that the test design was optimized. So again, like I said, this is rather than just kind of eyeballing it and going, yeah, item difficulties and discriminations are about the same across the modules. Like they actually used machinery that could handle this and give you the best possible estimates given some constraints.
Okay. Well, given that they're using CTT for the stages, did you ever think about looking at how misrouting affects like the model fit at the end? Like when we are estimating the parameters again?
No.
Okay.
Open question.
Mm-hmm.
I think maybe someone else has, but I haven't.
Okay, thank you.
Yeah, you're welcome.
I had the opportunity to look at the 2015 operational items in work that I was doing with Joan Herman on cognitive complexity. And so I know that they're constructed as testlets, and then sometimes the items can vary within the testlets. How much do you think that that plays a role in some of this misrouting that happens?
Can you say a little bit more? Okay, so, well, let me see if I understand.
Like there's a single stimulus, and then there's different items that can be like with that stimulus on the PISA test. And so
for reading?
For reading, math, science, like, but so they're kind of formed as like testlets. Do you think that that like has any role in the misrouting?
I think, well, okay, so the misrouting is, like I said, this is done at random. So you take your module of items, and if there is like a testlet, so there's a reading passage, and then 5 or 6 items, and then maybe that's the module, or 8 items, and that's the module. You have some performance on that, they calculate the number correct, and then you should either go high or low, but then there's a small probability that you're supposed to go high, but you go low. You're supposed to go low, but you go high. I mean, to the degree that there are between item dependencies, and you can leverage that information to get a higher score than you might have otherwise, I mean, sure. but I don't know what the impact would be. Monse, you looked a little bit at testlet stuff. I don't know if maybe you have some more
Well,
perspective on this.
on the context of PISA or Pearl, sorry, I'm looking at testlets, but I don't think so. The way they're trying to apply adaptive testing is very different. I wouldn't say it's the same idea that we have here with multi-stage testing or a fully computerized adaptive test. So that's an interesting question, though. In general,
Yeah, well, and if I
if the
remember right,
composition.
yeah,
Sorry,
based on
go ahead.
on the 2015, if I remember right, though, different items could be in the testlet depending upon how it got routed. But that was, it's been a while since I've looked at the operational manuals.
Well, in 2015 it wasn't adaptive.
Right, I know.
It was a linear test.
But
It was
some of those,
preset, right?
that's still the main design of the testlets with how like the items, could be in it has continued on. I know.
But those would be fixed. So there would have been like, you would get, although it would have been, I mean, some people take paper, some countries still take paper-based tests, but let's just focus on the computer tests. The forms are fixed in advance and you are randomly assigned to a form that once you get it, nothing changes.
Right, but I believe that sometimes on different places on the matrix, the form has different, it has the same stimulus, but different items.
Yeah, that's possible. Yes.
That's interesting. In Pearls, it's not the case. So you have pre-assembled and all the items, that belong to that reading passage remains the
stay.
same. Yeah. Thank you, Debbie. Daniel has a question. He says, what is the norm regarding item exposure and item overlap rates in this type of ILSAs?
So before they went to an adaptive approach, the exposure was equal across the countries. I don't want to go down the rabbit hole and talk about the exception that happened in a couple of cycles of PISA, but the general approach was like the forms are all the same for every participating country. So you all get the same item. So everything is exposed in the exact same amount. The exception that I didn't want to talk too much about is that in 2009 and 12, they gave countries that wanted them easier blocks of items. So there were, I can't remember the total number of blocks, but like six total, there were 6 total blocks of math items. And you could, if you wanted to, take the option to say, I want 2 of those blocks to be easier. So then those items for the easy block countries, again, even item exposure across the participating countries. And those items only are administered to those countries. And so those that participate, they would get them all evenly. So that was the norm. And so now there's been a lot of simulation work to guide like how often do we need to, or how much do we need to concern ourselves with every country getting all the items so that we get reasonable estimates of item parameters. And we've settled somewhere between like 20 and 30% of examinees should see a good selection of the items so that item parameters are reasonably estimated.
Thank you, Leslie.
Yeah.
If we don't have more questions, we can take one more, I think, for time reasons. But if there's no more questions, I just want to... Yes, indeed, everyone. Thank you so much for attending this talk. Thank you so much, Leslie, for presenting and opening the Brown Bag series sessions. To your question, Daniel, we will share the recordings. So I think that's we're gonna share slides and the presentation as well. Anyways, thank you so much again and have a good weekend, everyone.
Thank you. Thanks everyone for attending.
Thank
Bye.
you.
Bye.